This is the Test 3 review video covering, Chapter 12, that sampling distribution stuff, all the way to confidence intervals. Before we start on the test review, I just want to make sure that we're good and up and knowledgeable, I suppose, with the assumptions and the conditions of sampling distributions and things like that. Because you'll notice as we go through the review that a big chunk of problems, probably a quarter of the problems themselves, just deal with making sure that you know whether or not some of these statistical procedures and inference things that we're going to do actually apply. So I have some applets pulled up, and one of the things we're going to talk about is if you have a population that is normal, when is the sampling distribution normal or approximately normal? So what I have here is I have a population that is defined to be normal, and what we're just going to do is start sampling from this distribution. Basically sample let's see animated. Sample 5 things from that population and compute the mean. Sample 5 more things from that population, and then take the mean of those 5 observations and put them down here. And that's what a sampling distribution is. It's the collection of all possible sample means for a certain sample size. So I just want to do it real quick. Let's just do 10,000. We can do 10,000 more. We can do 10,000 more. Saying that we have 30,007 sample means in this distribution. What you should notice, though, is the shape. Our population was normal, and what you'll notice is that our sampling distribution is normal. So in the wordings of these problems, if it says that the population is normally distributed, we can automatically assume that the sampling distribution is normal, regardless of the sample size. You'll notice that I only sampled 5 observations at a time. I know there's that rule where it has to be bigger than 30, but that doesn't apply here because our population is normal. But we can do it again. Let's just do some sort of skewed distribution. That's clearly not normal. And what you'll notice here is that if I sample 5 observations at a time, and 5, let's just do 100,000. It looks kind of normal. It looks approximately normal, but it's actually not. You'll notice here, I have 700,000 observations here. What you'll notice is that this distribution is still slightly skewed right here. So what we have is that rule that says we need this distribution to be approximately normal in order to make these probability and inference calculations. So let's just bump this sample size up to 25. And let's just do the same thing. Our population is still skewed. It's not normal. And we're just going to take various sample sizes. So what you'll see here is I have 600,000 observations plotted in this distribution. But what you'll notice is that this is normally distributed, the sampling distribution. And also, I didn't say this before, but the means of both groups are the exact same. The mean of the population, even though it's skewed, and the mean of the sampling distribution are in fact the same. So this is when you get into that rule where if the population is not normal, how do we guarantee that our sampling distribution is normal? Well, we just make sure our sample size is at least 30. All right, so with means, we have 2 criteria. One is that if our population is normally distributed, our sampling distribution is automatically approximately normal due to, or regardless of the sample size. But when we have other populations here, I can make one up. Let's just do, we'll just do this. Something weird. There we go. Heavily skewed left with some bumps up there. Trimodal. And let's just do sample sizes of 5. So remember, we take 5 observations from the population and plot them. And we're just going to do that, a few times. And you'll notice this looks symmetric. It looks approximately normal, but once again, we're still skewed a little bit here. So our probability calculations are going to be slightly off than what we need them to be. using the normal distribution. So if I change my sample size to 25 and do this again, there's our normal distribution. All right? So even though the population is super, super ugly, our sampling distribution, when we have a sample size of at least 30, I know I have 25 here, but I can't do 30 on this app. It makes it approximately normal. That way we can answer questions about the population as a whole. Going to proportions. So with proportions, one of the things we have to guarantee for approximately normal sample distribution is that n times p and n times 1 minus p were at least 10. So let's just define our probability as 0.6. And we're going to say, let's sample 5 at a time. I don't want to animate. And this is draw a sample. We're going to draw one sample. And there's our sample proportion. Slightly here, I guess. Oh, this is the number that we drew. Not the proportion, but it's the same thing. And what you'll notice, let's just do 100. If I do this, if I define n to be 5 and p to be 0.6, once again, we get this distribution here that while it looks normal, it actually is not. It's still skewed a little bit because we're having this, mode here, but then we're kind of pulling off to the left. So one of the things that we had to guarantee was that n times p and n times 1 minus p are both at least 10. So let's just define let's just make our sample size 30 again. And let's just do it again. Oh. And what do you notice? It's a little bit better. So one of the problems that you're going to have to see, or one of the problems you're going to see when we do these calculations is, are the conditions met to make these inferences? And you have to check if it's a mean, whether or not the population is normal. If it's normal, then yes. If it doesn't say anything about the population, or if it says it's skewed, our sample size has to be at least 30. That's for means. With proportions, what we need is that n times p and n times 1 minus p have to be at least 10. So in this case, n times p is 18. Oh, look, there's 18. That's what I mean. So 30 times 0.6. That means that we have at least 18 successes. N times 1 minus p would then be 12. They're both at least 10. I mean, we don't have to do this. We could do 0.4 if we wanted to, or 0.2. Let's sample 100 at a time. Draw samples. There it is. We can just keep on going. My computer's having trouble keeping up with the number of samples. But then we see it's more symmetric there, and we can just keep on going. But this allows us to conclude that the sampling distribution is approximately normal so that we can make these probability calculations. So, to the test review. All right. In June 2015, Gallup poll conducted a poll of a random sample of 14,754 adults to determine the well-being of people living in the U.S. One question asked, did you exercise for at least 30 minutes? In the survey, 58.3% of males and 41.7% of females responded yes. Which of the following is true? 58.3 and 41.7 are both parameters. That is not true. Parameters are values that describe the population. We are doing sampling distribution and confidence intervals to estimate the unknown parameter. We estimate those unknown parameters with statistics that we calculate from a random sample. If we took another random sample, we would expect to get the exact same results. That's not true either. Think about if I went to the movie theater and asked people what their favorite movie was, and the majority said Infinity Wars. If I went to a different movie theater and I asked people, would you think that we would get the exact same results? Depends on where you go. It's called sampling variability. But 58.3 and 41.7 are both statistics. That is true. We calculate those using the sample, and we make inferences on the population using it. So, same type of question. So they conducted a survey of 1,481 U.S. adults Would you like to see the Supreme Court completely overturn its Roe v. Wade decision? The results were 26% said yes, 66% were no, and 8% were unsure. But because these values were conducted and calculated using the sample, they're statistics. A social scientist wishes to conduct a survey. She plans to ask a yes or no question. One proposal is to select 100 people. Another proposal is to select 900. Which of the following is true regarding the sample proportion of yes? The sample proportion of the sample of 900 is more likely to be close to the true proportion. The sample proportion from a sample of 100 is more likely to be close to the true, equally likely. So, one of the things that you might have seen is that increasing the sample size, this might work, let's just see. My computer can't keep up. Let's just do the main one. Keeping up with the sample size, increasing the sample size actually reduced the variability in the sampling distribution. So if I did a sample of 50, it would be more mushed in, I suppose how to describe it. So increasing the sample size reduces the variability, which means that most of our values are closer to the actual mean. So the sample proportion from a sample of 900 is more likely to be close to the true population proportion because increasing the sample size reduces the variability. This is the exact same question. So, which of the following is true? The sample proportion of 1600 is more likely to be close because the higher the sample size, the less variability. Okay, if the study were conducted repeatedly, so one plan is to select 400 voters, the other is 1600. If the studies were conducted repeatedly, selecting different people, which of the following would be true regarding the sample proportion of yes? Different sample proportions would result each time, but for sample size 1600, they would be centered at the true population proportion, whereas the sample size 400 would not. Well, I'm going to say that which replacement? No. D is not true. Different sample proportions would result each time, but for either sample size, they would be centered at the true population proportion. Yeah. I would say that's probably true. Different sample proportions would result each time, but for either sample size, they would be centered at the true population proportion. I would say because your sample sizes are still so big, they both would be centered where they need to be centered, but the variability of the 1600 sampling distribution would be smaller than the sampling distribution for the 400 group. Same exact question. We have a group of 100 and a group of 90 people. You know, we're talking about proportions here, so with a sample size so big, we're basically guaranteed that n times p and n times 1 minus p are going to be at least 10. So, different proportions would result each time, but for sample size 900, no. I would say D again. Different sample proportions would result each time, but for either sample size, they would be centered at the true population. Wait. Yeah. Okay. Juries should have the same racial distribution as the surrounding communities. According to the U.S. Census Bureau, 18% of residents in Minneapolis are African Americans. So the local court will randomly sample 100 state residents and will then observe the proportion in the sample who are African American. How likely is the resulting sample proportion to be between 0.066 and 0.294? Well, if you look at your answer choices, 99.7, 68%, 95%, those are the standard deviation values. Within one standard deviation, you're within 68%. Within two, it's 95, 3, 99.7. So what we want to do here is let's calculate the standard deviation of the sampling distribution in this case. So one of the formulas that you have to know is that the standard deviation of the sampling distribution for a proportion is the square root of p times 1 minus p over n. So 0.18 times 1 minus 0.18 divided by 100. You might just type in like that. Just make sure you put parentheses around the 1 minus. Hit enter. So there's your standard deviation of the sample proportion. So if we go 1 standard deviation to the left of the mean, so the mean is 0.18. So 0.18 minus our standard error, our standard deviation, we get 0.14. 0.18 minus or plus that, we're at 0.218. All right, well that's not close. That's not the values we need. So let's do 2 standard deviations. I'm just going to go in the code and just do 2 times. And then go up there and do 2 times again. Still not quite what we need. Let's just see what happens when we go 3 standard deviations away using our, and there it is. So there's what we need. It's slightly off, 0.065, due to rounding. But the idea is that 3 standard deviations away give us 0.066 and 0.294. So there is roughly, standard deviation rule says within 3 standard deviations, there is roughly 99.7% chance that the resulting sample proportion will be between those 2 values. Which of the following best describes the sampling distribution of a statistic? Is it a distribution of all parameters? Nope. It's a distribution of a single statistic from repeated random samples of the same size from the same population. There you go. Distribution of a single statistic from repeated samples of the same size from the same population. So as 20% of the residents in a certain state supported an increase in the property tax, an opinion poll will randomly sample 400 state residents and will then compute the proportion in the sample that supported property tax increase. How likely is the resulting sample proportion to be within 0.04 of the true proportion, between 0.16 and 0.24? Well, let's just see what our sampling distribution standard deviation is going to be. So the square root of p times 1 minus p over n. Well, in this case, our p, our population proportion, our parameter is 0.2. 1 minus 0.2 over 400. So that means our standard deviation is 0.02. So then let's just do what we did before. Let's just see how many standard deviations away from the mean these values are. So if I go, our population parameter, 0.2 minus that standard error that we just calculated, and plus I get 0.18 and 0.22. We want 0.16 and 0.24. So that tells us we need to go a little bit further. Let's see 2 standard deviations away. Oh, there's our 0.16. There's our 0.24. So those values are 2 standard deviations away from the mean, which according to the standard deviation rule, there's roughly a 95% chance. A distribution of a single statistic from repeated random samples of the same size from the same population refers to the sampling distribution. You gotta know that definition. Alright. A social scientist wishes to conduct a survey. She plans to ask yes or no questions. One proposal is to select 900, and the other proposal is to select, 100 first, then 900. Which one of the following is true regarding the standard deviation? Okay, let's just make up some numbers. If you don't know, if you can't see this right now, let's just make up some numbers. Let's say p is equal to 0.2. We'll just keep that value. And we're going to calculate 2 standard deviations here. One when n is 100, one when n is 900. So if we calculate the standard deviation, it's the square root of p times 1 minus p, so 0.2 times 0.8 divided by 100. We get 0.04. Let's just see what happens when we divide by, or when we have our sample of 900. Square root of t times 1 minus t out of n. 0.01333. I was trying to ask, what is 0.04 divided by 3? And it's an equal sign. Oh, there it is. So, what does that mean? Well, increasing the sample size by a factor of 9 reduced the standard deviation by a factor of 3. It would be 3 times smaller. And that should make sense. Remember, we talked about a little bit ago, increasing the sample size reduces the variability. So if I increase my sample size from 100 to 900, we should have a smaller standard deviation. The question is, how do we know that it's reduction by 3? Well, if you think about your standard deviation formula, this standard deviation, or this sample size, is 9 times the smaller one. Think about a square root. That's what we're doing when we do the standard deviation. What's the square root of 9? It's 3. So we're going to be reduced by that factor. So the standard deviation of the sampling distribution will be 3 times smaller with sample size. It will be 3 times larger with sample size 100. Pay attention to the wording. So with 900 it was 0.01, 33323. For 100 it was 0.04. The 900 is a smaller standard deviation, which means that the standard deviation is larger for a sample size 100 by a factor of 3. Here we go. One plan is to select 400, the other plan is to select 1600. So let's just talk really quickly about just reasoning through. We don't have to calculate, but then we will calculate in a second. So go from 400 to 1600. I've multiplied the sample size by 4, which means that what's the square root of 4? 2. So this standard deviation will be 2 times smaller than the 400 sample size. The larger one's always smaller. But these is all in terms of the sample size of 400, so we will know that it will be 2 times larger with sample size 400. And if we go back to the other thing right here we've done, let's just change this to 400 and 1600, and you'll see it's going to be double what the other one is. So, hello, 400, and then 1600. 0.01. Don't worry about it. So when the sample size is 400, our fake data has a standard deviation of 0.02. When the sample size is 1600, it's 0.01. It's 2 times larger. Okay. In a study of the effects of acid rain, a random sample of 100 trees from a particular forest is examined. 40% of these show some signs of damage. Which of the following statements is correct? More than 40% show sign of damage, less than 40, we don't really know that. We can't claim anything about that. But what we do know is that 40% is a statistic. That's what we got from that sample of 100. In a study of the effects of acid rain, a random sample of 100 trees from a particular forest is examined. 40% of these show some signs of damage. Which of the following is correct? If we took another random sample of, I skipped none of the above. You know that. None of the below. If we took another random sample of trees, we would find that 40% of these would show some signs of damage. Nope. Sampling variability tells us that another sample would likely have a different value. The sampling distribution of the proportion of damage to trees is approximately normal. And this is a comparative experiment. If a sample of 1,000 trees is examined, the variability of the sampling proportion would be larger. Well, we know that's not true. So, I'm going to say it's probably C, because with a sample size of at least 100, we're meeting that n times t times n times 1 minus t criteria. Okay. Oh, let's save. Oops, too far. Way too far. Question 15. Okay, here we get to the fun stuff. Okay. Blah, 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 blah. Survey asks a random sample of 1,500. So n is 1,500. You'll see with most of these problems, like mark off certain blocks in Excel. Because once you're able to do most of these questions, the formulas are the exact same. So I'm just going to change the numbers and just automatically be given the answer. I'm probably not going to do every single problem from start to finish. You know. So, if they support a sales tax increase, let P denote the population or the proportion 14%. So what's the standard deviation of the sampling distribution? So we know that the standard deviation is the square root of P times 1 minus P over N. We're going to round this to 4 decimal places. And what's nice though is, oops, too many. What's nice is that if you do it this way by just marking off cells and just clicking them, if another question that's similar appears in the test, you already have all the code done and you just have to change the number. There we go. Okay. Suppose that number 16, suppose that 78% of all dialysis patients will survive at least 5 years. In a simple random sample of 100, what is the probability that the proportion surviving will exceed 0.8? So in this case, our n is 100. P is 0.78. And here, look what happened. It automatically calculated the standard deviation. It automatically, because of the way that I defined it, I'm going to move that up a little bit though. It automatically calculated n times P times 1, or n, or I can't talk, P times 1 minus P over n to the square root. So we need that value though to answer the question. So we want the probability that if we sampled, our sample proportion will be at least or exceed 0.08. So that's what we're looking for. So think about this. Is our sampling distribution approximately normal? So we would want to calculate n times P and n times 1 minus P. We know it's going to be met here because it just wants the probability. This isn't a check the conditions thing, but it is important to kind of consider. So if we do n times P, we get 78. If we do n times 1 minus P, we get 0.22. They're both at least 10. So we know the sampling distribution of this sample proportion is approximately normal. So we can answer these probability questions using norm diff. So in order to use norm diff, though, we need to calculate a z-score. So let's look at z. So if you remember from our formula, it's going to be x minus the mean over the standard deviation. So in this case, though, our x value, if you look below, is 0.8. We're going to use that. We're saying what is the probability the sample proportion will exceed that value? What's the mean? 0.78. That's what we're defining as our population proportion. So 0.8 minus 0.78 divided by the standard deviation. Well, we calculated that before. Square root of P1 minus P over N. There's our z-score. And now when we do our normal calculation, all right, let's just think. We want a greater than probability. So you should remember from test 2, when we use norm diff that involves a greater than, we have to do 1 minus. So we do 1 minus norm diff or norm S diff. I'm going to do norm S diff since we calculated the z-score already. And then just click the z. Cumulative is always 1. Done. And we want rounded to 5 decimal places. 1, 2, 3, 4, 5. 0.31462. Okay. Which of the following statements about the sampling distribution of the sample mean x bar is true? The distribution is normal regardless of the shape of the population, as long as the sample size n is large enough. That is true. Typically, if you're doing 30. The distribution is normal regardless of sample size, as long as the population is normal. That is also true. The distribution's mean is the same as the population mean. That is also true. The distribution standard deviation is smaller than the population standard deviation. That is also true, because our formula for the standard deviation of the mean is the population standard deviation divided by the square root of n. We're dividing by the square root of the sample size, which reduces the variability. It's weird that all of them are checked. Does it ever make you weird when you do that? Those are all right, but it's just weird to me. The distribution is normal, regardless of the shape of the population distribution, as long as the sample size is long enough or large enough. The distribution is regardless of the sample size, as long as the population is normal. That's true. All right, I'm going to go with all four of those. Suppose we take repeated random samples of size 20 from a population with a mean of 60 and standard deviation of 8. Which of the following is normal? Which is the following? Okay. The distribution is normal. Okay, the distribution regardless of the because the sample size is large enough. That's not true. We typically say it's 30 or more. The distribution will be normal as long as the population distribution is normal. Yep. The distribution's mean is the same as the population mean. That's correct. And the distribution standard deviation is larger than the population. That's not true. The sampling distribution has a smaller standard deviation, smaller variability. So it's just B and C. Number 19. Pictured below in scrambled order are 3 histograms. One of them represents the population distribution. The other 2 are sampling distributions of X bar, one for size n equals 5 and one for size n equals 30. Okay. Based on the histograms, which is the most likely value of the population mean? Well, let's just look at which one is approximately normal. Histogram 3 is skewed, histogram 2 is skewed, but histogram 1 is not. Histogram 1, then, if you think about the central limit theorem and what it says about the sampling distribution, n equals 30, that tells us it's going to be approximately normal. What is the mean of this distribution? 3. So the mean of the sampling distribution and the mean of the population are the same, so it looks to be about 3. And then this one's also centered at 3, just a little bit more varied, kind of emulates the population more so than the other one. Okay, pictured below are 3 histograms. One of them represents a population distribution. The other 2 are sampling distributions, one for size 5 and one for size 40. What is the mean? Look at the one that's most normal. That would be the one for sample size n is 40. And where is it centered at? Just about 8. Hey, you go. All right. Suppose that a candy company makes a candy bar whose weight is supposed to be 50. But the weight varies from bar to bar according to a normal distribution with mean 50 and standard deviation sigma equals 2. Think of it like a potato chip bag. Sometimes you get a potato chip bag that has a whole bunch of chips in it because it has to meet some specified weight. But then you get some that have like 1 or 2 chips in it and you're feeling really bummed. That's kind of like that. It varies. So if the company sells the candy bars in packs of 4, what can we say about the likelihood that the average weight of the bars in a randomly selected pack is 4 or more grams lighter than advertised? So, this is for mean. So, we can define our sigma. Let's just find population mean. I'll say mean is 50. Hello, 50. Sigma is 2. Let's calculate first the standard deviation of the sampling distribution. That's going to be sigma. Oh wait, let me define n also. N is 4. Standard deviation. I'm going to interchange the word standard deviation of sampling distribution and standard error quite often. That's what it's defined to be. The standard deviation of the sampling distribution is called the standard error. I'm going to take, so anyway, standard deviation for the sampling distribution of a mean is sigma divided by the square root of n. So sigma over the square root of 50. Nope, of 4, sorry. Sigma over the square root of n. 50 is the mean, not. So our standard deviation is 1. So we want, what is the probability or the likelihood that the average weight of the bars is 4 or more grams lighter than advertised. So we want less than 4 or more grams lighter. So that means we want less than 46. Because 4 grams lighter than what's advertised is 46. So we want 4 or more grams lighter. Yeah, so less than 46. So before we do that, let's just calculate the z-score. The z-score is defined to be our value of x, 46, minus the mean of 50, divided by the standard deviation. So negative 4. So, remember, z-scores can be negative. That's not wrong. It just means we're 4 standard deviations to the left of the mean. So, because our population is normal, our sampling distribution is normal, even though the sample size is so small. So we want less than, to approximate normal, we use norm S diff. Remember, norm S diff will automatically calculate less than probability. We don't have to worry about 1 minus. Norm S diff, Z1 is always the cumulative. I'm just going to say this number is going to be very small. And there it is. Remember, when you get this number, that does not mean it's wrong. That's scientific notation for move the decimal to the left 5 times. So 0.00003, which is very small. So it is extremely unlikely for this to occur. It probably is very close to 0, which is true. Okay, suppose that a candy bar company packages whose weight is supposed to be 30, so it varies normally. I'm just going to change the numbers here. That's why I think just typing it in the way that I'm doing it is so helpful, because if there's a problem that's very similar to another problem on the test, typing it this way, you just have to change the numbers. But making sure you type it in right, because if you mess up on one of them, you're going to get the second one messed up. So the mean of this distribution is 30, standard deviation is 3, our sample size is 9, and a company sells the jelly beans in packs of 9. And look at that. It's calculating everything for us. Be careful, though, because our Z and stuff is different. So we want, what is the probability that the average weight of the bags in a randomly selected pack is 2 or more grams lighter than advertised? So we want, then, is less than, it's advertised to be 30, 2 or more grams lighter than less than 28. So that means we go back to our z-score, we want 28 minus 30 over 1. So, it automatically calculated our z-score, or it calculated our z-score for us by just changing the number. Because we already have this whole thing typed in, it automatically calculated our probability, norm S diff. So, this is 2.3% chance. So, we can even multiply this by 100 if you want, if you guys struggle with seeing the similarities. About 2.275, we're going to say that's about 2.5% chance. I think when they made these questions, they made it so that you could potentially use the standard deviation rule because your standard deviation is 1. And so, yeah, you can do it that way. But I would just use norm diff. Remember, the standard deviation rule is an approximation. And one question coming up, we're about to talk about how it's not 95% of the data is not exactly within 2. It's actually 1.96 standard deviations. But our exact value is 2.275. The standard deviation rule will tell you it's 2.5. They're very close. It's an approximation. When the population is not normally distributed, the sampling distribution of the mean approximates which of the following? A normal distribution with a large enough sample. There we go. In which of the following scenarios would the distribution of the sample mean x bar be normally distributed? We take repeated sample sizes of size 10 from a population of unknown shape. No, not big enough. We take repeated random samples of 15 from a population that is normally distributed. Yes. Remember, if the population is normal, the sampling distribution is normal. We take repeated random samples of size 50 from a population of unknown shape. Yes. And we take repeated random unknown shape. I'm going to go ahead and say that we're not going to select D because really we want the sample size to be at least 30. So I'm going to say it's just B and C. Even though 25 is close to 30, I'm going to say it's just not that one. All right. A factory produces glass or plate glass with a mean thickness of 4 millimeters and a standard deviation of 1.1. Okay, let's just. Mean is 4. Sigma is 1.1. A sample of 100 is to be computed. Look, I'm just going to still type the same code that I did before. It's going to be the same. Of 100, that means the standard deviation of the sampling distribution is on that. We calculate it for us. Sigma over root n. What is the probability that the average thickness is less than 4.03? So, what we need to do is first calculate our z-score. To make this a little bit easier, let's just, that's fine. We'll just go this way. So we're going to do our z-score first. So we want less than 4.03. So we're going to do 4.03 minus the mean divided by the standard deviation that we calculated earlier. That's our z-score. Let me just make sure I calculated it right. Sigma over root n, 1.1 over b11. Yes. So then, less than 4.03 means our z-score is less than 0.2727. Well, let's save really fast. Every time it asks you to save, please do not click cancel. Please, 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 please save it. Alright, so anyways, because we're less than, we use norm dist or norm s-dist. Because I calculated the z-score, I'm going to use norm s-dist. Click the z-score, cumulative is always 1. And we want rounded to 5 decimal places, which it is 0.60747. Question 26. The number of hours a light bulb burns before failing varies from bulb to bulb. The distribution of burnout times is strongly skewed to the right. The central limit theorem says that. So the central limit theorem is what allows us to conclude that the sampling distribution will be normal when the sample size is large enough. So the average burnout time of a large number of bulbs has a distribution of the same shape. Nope. The average burnout time of any number of bulbs has a distribution of the same shape. Nope. The average burnout time for any number of bulbs has a distribution that is close to normal. For any number of bulbs. Nope. As we look at more and more bulbs, their average burnout time gets closer to the mean for all bulbs of this type. That's more, letter D is more the law of large numbers. As you increase the sample size, this average will get closer and closer to the population average. But the central limit theorem really deals with the shape of the sampling distribution. So E, the average burnout time of a large number of bulbs has a distribution that is close to normal. There we go. Question 27, everybody's favorite question. It was number 7 on the sampling distribution of 2 checkpoints. A machine is designed to fill 16-ounce bottles of shampoo. When the machine is working properly, the mean amount poured into the bottles is 16.05 with a standard deviation of 0.1 ounce. If 4 bottles are randomly selected each hour, and the number of ounces in each bottle is measured, then 95% of the observations should occur in what interval? This is a really badly worded question. I'm actually not going to lie, just to avoid anybody taking the fault. I typed this in here. I made this question, but I didn't type everything I needed to, so I apologize. It really should say that the amount poured into the bottles is varies or is approximately normal with mean 0.6 or 16.05 and standard deviation 0.1, because the sample size 4 is super small. We really should say the amount poured is approximately normal. So, in this case, though, the mean is 16.05, and sigma is 0.1. What this question wants, though, it's not that much of a stretch. It asks you for 95% of the observations should occur in what interval? Well, that's just the standard deviation rule. Remember, 95% of our observations occur within 2 standard deviations of the mean. But we're talking about the mean of the sample means. We're talking about the sampling distribution. So it's not 16.05 plus or minus 2 times 0.1. We need to first calculate the standard deviation of the sampling distribution, which is sigma over the square root of n. Another issue with this question is that it's using the more exact value. I said a little bit ago that this question will not be on the test, by the way. So 95% of our data is within 2 standard deviations of the mean, according to the standard deviation rule. Well, the standard deviation rule is an approximation. The exact value is 1.96. And I don't know why. I don't remember typing in 1.96 when I did this problem. I used 2, but it's only counting it right if you use 1.96. So we're just going to do that. So we're going to calculate 1.96 standard deviations to the left and to the right of the mean. So 16.05 minus 1.96 times the standard deviation. And then 16.05 plus 1.96 times the standard deviation. And really, what you should notice is that we just typed the formula for a confidence interval. 1.96 is the z-score that corresponds to 95% confidence. It really does tie the standard deviation rule together with this, though. So, 15.952 to 16. Oh, I do 4 decimal places, huh? Oh, never mind. 148. Okay. Number 28. Suppose that the distribution for total amount spent by students vacationing for a week in Florida is normally distributed with a mean of 650, standard deviation of 120. Suppose you take a simple random sample of 50 students from this distribution. So 50 students is large enough, according to the central limit theorem, to claim that the sampling distribution is approximately normal. So to get our standard deviation of the sampling distribution, remember standard error, standard deviation of sampling distribution are the same thing. We take sigma divided by the square root of n, and that's where that 16.97056.275 comes from. But what we want is the probability that we spend within 600 and 700. This gave a lot of students issues as well, because you forgot how to do this from the last test. So we basically have to find the probability that x is less than 700 minus the probability that x is less than 600. We just do 2 different norm dist calculations. So I'll show you that this is probably easier just using norm dist. So we want to do, when x is 700, the first one, with a mean of 650, but a standard deviation of that 16.97 something, cumulative is 1. That tells us the probability that we're less than 700 minus, do another norm dist, when x is now 600, mean is 650, standard deviation is once again that 16.97, blah, 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 cumulative is 1. And I do it this way with this question because I don't want to calculate 2 different z-scores. Because if we calculated the z-score for 700 and the z-score for 600, we could then use norm s-dist. It doesn't matter, but there it is. 1, 2, 1, 2, 3, 4, 5. There's our probability. 0.99678. Alright, number 29. The admin at GSU wants to estimate the number of parking spaces they will need next year. They surveyed 80 students. 75 of the students in the sample drive to campus by themselves. Which of the following is a reason the administration should not calculate a confidence interval? So the sample needs to be random, but we don't know that it is. That's also true. It needs to be a random sample. It doesn't say anything. They just say they sample. The actual count of drivers is too small. So this deals with the n times p and the n times 1 minus p criteria. So the number of successes needs to be at least 10, and the number of failures needs to be at least 10. But we know that 75 out of the 80 drive, so that's not true. That's at least 10. But that means that there are only 5 people who don't drive. That's too small. And that means n times 1 minus p hat is not greater than 10. Concert marketing, not going to do the whole thing, but out of 110 people surveyed, only 7 received the concert. So, actually I do need to read it because I need to see it. from a survey. We don't know if it's random. The actual count of residents who received the concert brochure by mail is too small. That's true. We need at least 10. That means that 103 received it, which is bigger than 10. So that means n times p hat is not greater than 10. Okay, a statistics student used the information from the poll to calculate a 95% confidence interval. I actually have to read this one. An interactive poll on the front page of CNN website in October 2011 asked if readers would consider voting for Herman Cain, who at the time was a Republican presidential candidate. He calculated confidence interval, but I would say that, let's see, the results do not apply to the volunteer response sample. They apply to the population of those who visited the CNN website where the poll was on the front page. Well, we have to kind of think about what population that we're looking at here. And that means that we have to also think about how this data was sampled. So one of the criteria is that in order to do a confidence interval, the data has to be from a random sample. Because the poll is just on the CNN website, really the only people that are going to respond to that type of sample or the type of that poll are going to be the ones that feel strongly about it. That's a voluntary response sample. It's not random. So therefore, we can't generalize these results. So let's see. For our class assignment, a group of statistics students set up a table near the student parking lot. They asked students who pass by to complete a quick survey about whether they support the building of a multi-level parking structure that would add 425 new spaces at college. This is a convenient sample, so I'm just going to go ahead and say that it does not apply. They're asking people who park in that deck. Listen, I park in N deck, and if there was somebody with a table out and saying, do we need more spots there, I would wholeheartedly say yes. But I'm biased because on Wednesday mornings when I park there, there are no spots. So it just makes me angry. So, same idea. Okay. Confidence interval, calculating them. We've actually already we have all the information we need to calculate a confidence interval. I'm just going to erase all of this stuff. Okay. In a recent ABC News Washington Post poll, our sample size is 1,364. Of the respondents, at 491 support it. So, what is the proportion? We're looking for the proportion who support same-sex marriage. So P hat, that's what's going to be our X over N. So in the sample, about 36% of people support same-sex marriage. So from P hat, we need to calculate the standard deviation, the standard error. Standard deviation error, same thing. So we know that that's going to be the square root of P hat times 1 minus P hat divided by N. That's your standard error. But with confidence intervals, it's kind of like the standard deviation where we need to kind of look at a z-score. So the z-score for 95% confidence is 1.96. And most of these will be given to you, but just in case you want to know, 99%. So a 90% confidence has a z-score of 1.64. 95 is 1.96, and 99 is 2.5758. If you want to memorize them, they're on the formula sheets and stuff, but that's not 1.93, 1.96. Wrong question. So, we need to calculate now the margin of error. The margin of error is just your z-score times your standard error. So really, we're going 1.96 standard deviation to the left and to the right. So that means our lower bound and our upper bound we can specify now as P hat minus the margin of error and P hat plus the margin of error. To give us a confidence interval that ranges between 0.334 and 0.385. But look at how we type all this in. We just clicked all of our values. So all we have to do to keep doing these remaining confidence interval questions is just change the numbers that we've already specified. Excel will automatically and quickly change the numbers. So another sample has a sample size of 1,380. X in this case is 472. And look, it automatically calculates p-hat. It automatically calculated our standard error, p1 minus p over n, square root of that. 95% confidence is a z-score of 1.96. And then everything else is now done. We calculated our margin of error by doing the z-score times the standard error, and then we did our p-hat minus the margin of error, p-hat plus. So, looking at the values there, our confidence interval is 0.317 to 0.367. Okay, another one. Suppose we take a poll of 3,512 classified as juniors, and we find that 3,167 of them believe they will find a job immediately after graduation, which means about 90% of them believe that. Our standard error is p-hat 1 minus p-hat over n. We want a 99% confidence interval. Well, that's going to be 2.5758. Some textbooks should say 2.58. And there we go. And we do p-hat minus the margin of error, p-hat plus the margin of error to give us 0.889 to 0.915. Okay. In the months leading up to an election, news organizations conduct many surveys to help predict the results. Often, news organizations will increase the sample size. Which of the following is the primary reason they increase the sample size? Well, increasing the sample size, as we talked about, decreases the variability of the sampling distribution. What that means in terms of a confidence interval is that it makes it narrower. We want a narrower confidence interval because that interval gives us the plausible values of the population parameter that we're interested in. In the case of an election, it gives us the plausible values for the percentage we're going to vote for a particular candidate. So a larger sample size means that the sample, no. It just means a narrower confidence interval. Okay. We know that narrower confidence intervals give us a more precise estimate of the true population proportion. Which of the following could we do to produce a higher precision in our estimates? We could select a lower confidence level and increase the sample size. So, first of all, more precise means smaller sample size. Or larger sample size, I'm sorry. More precise means larger sample size. So, it's going to be A or D. We can not count B or C, because increasing the sample size is higher precision. But we also have to then say, do we lower the confidence or raise the confidence? Well, if you look at these values of Z for these confidence levels, if we want a narrower confidence interval, that means that we want a smaller degree of confidence because our multiplier is smaller. So we select a lower confidence but a higher sample size. All right. A group of statistics students conducted a survey about smoking habits on campus. Of the 50 students surveyed, 45 think that smoking hookah is less harmful than smoking cigarettes. Which of the following is a reason that this group of students should not calculate a confidence interval? Well, look at, we don't know if it's random. And we believe that, and we have 45 successes. We have 45 who think it's less harmful, but that means we have 5 who think it's more harmful. And that means that n times 1 minus t is not greater than 10. Same as before. All right, I'm not doing 39 because I've just done it a lot. Look at that sample size of 4, or that 4 successes. So just keep that in mind. Okay, question 40. In a Pew Research Center report from January 2015, 30% of American adults say that genetically modified foods are generally safe to eat. The margin of error for the 95% confidence interval is 3.1. What does the margin of error tell you about the results of the survey? We are 95% confident that the sample proportion is off by 3.1%. We are confident that 95% of the responses are within 3.1 of the population proportion. We are 95% confident that the population proportion is within 3.1% of the sample proportion. That's how we calculate the confidence intervals. We take our sample proportion, add and subtract the margin of error. So it's C. It looks like D, but we have to specify the confidence level. Okay? The 95% confidence interval here is this. Which of the following is an appropriate interpretation of the 95% confidence interval? So, let me see if there's I just want to do, just to show you, confidence interval calculator, or applet. Here we go. Simulating confidence intervals. Go away. Here's what our confidence interval is. So we can do proportions if we want to. We can specify our value of the population as 0.6. And let's just, confidence level is 95. We're going to calculate one interval. So what this means, if the interval is green, it means it captured the true value of the population. But we know from sampling variability that these intervals are going to differ. So like in this one, we've calculated now 6 intervals, 5 of them met the criteria, or 5 of them contained the true population parameter, but this one, the 6th one we calculated, this one did not. That's the whole idea of confidence. We have to have some level of confidence to assert that the interval that we calculated actually contains the population parameter that we're trying to estimate. And so, let's just do 100 intervals. So we've calculated 100 intervals right here. And if you look, let's just do it again. Let's just keep going. So you notice we still have some green, mostly green, some red. We've calculated 100 intervals. In this case, 97 of them contained the true value of the parameter. If you look at our running total, though, it's keeping track of every interval we've calculated. Let's just make it up to 4,000. What do you notice about the percentage that contain the true population parameter? Well, of the 6,506 intervals that we've calculated, 94.5% have contained the true parameter that we're interested in. That's not a coincidence that we've specified our confidence level as 95%. So, an erroneous way of interpreting a confidence interval is to say, oh, there's a 95% chance that it contains the true parameter. That's not true. It means out of many, many, many intervals calculated using the same method, 95% of the intervals calculated will contain the true parameter value that we're interested in. Oh, let's save. So just, that is the correct way of specifying these. So that's, where are we? We're question, I don't even know what question we're at. They're 41. So, we can be 95% confident that the proportion of all cell phone users who use text messages is between 73.1 and 76.9. There isn't a 95% probability. It's not about the sample. We're generalizing and using the confidence interval to estimate the proportion of all cell phone users. So just be careful. The margin of error, okay. The Pew Research Center surveyed cell phone users about voice calls and text messaging. They found that 55% of those who send 51 or more text messages per day prefer to be contacted by text message rather than voice call. The margin of error is 5.7. What does this margin of error tell you about the results? The population proportion is likely within 5.7% of the sample proportion. And it's not, we are sure, because as we saw, some confidence intervals do not contain it. We have to be, it's likely. All right. The 95% confidence interval for this is 0.58 to 0.64. Which of the following is an appropriate interpretation of the 95% confidence interval? Well, there is 95% probability. Nope. We are 95% confident that the proportion of the samples. Nope. Of the samples, 95% will have between. Nope. We are 95% confident that the proportion of all Americans who said that race relations in the country are generally bad is between 58 and 64%. There you go. I'm not answering question 44. It's the same thing. Question 45. A hypothetical distribution for a population of test scores is displayed below. Its skewed left has a mean of 68 and standard deviation of 12. Each of the other three graphs labeled A to C represent possible distributions of sample means. Okay? Which graph best represents a distribution of sample means of 500 samples of size 4? Well, because we're doing a sampling distribution, let's see. We automatically have lower variability than the population. So if you look at this third histogram here, that looks just like the population. But because our sample size is so small, it's still going to display those characteristics of the population. In other words, it's still going to be skewed. So letter B here means our sample size is probably at least 30. So I'm going to say that because it's a sample size of 4, it has less variability than the population, but it's still going to display those common characteristics. So it's going to be graph A. All right. We have a population that's skewed right. The population has mean of 40 and standard deviation of 3. Each of the three graphs labeled A to C represent possible distributions of sample means. Okay. Which graph best represents a distribution of sample means for 600 sample size, each with sample size 5? Well, same thing. This graph here has means it's so close to, has such less small variability that it's probably a high sample size. So it's not going to be A. Graph B, to be honest with you, that doesn't even really look like the population, so I'm going to go ahead and say that it's probably going to be C. It seems small, but to me it seems weird that you would sample and then the skewness would change. Yeah. Let's see. That's approximately normal. Yeah, I'm going to stick to C. Because your skewness should not change based on the sample. Alright, question 47. Consider sampling heights from a population of all female college soccer players in the U.S. Assume the mean height of female college soccer players is mean 67, standard deviation 3.3. Suppose we randomly sample 96 values from this population and compute the mean. Then repeat this 5,000 times. Which of the following is the best approximation for the mean of our 5,000 sampling? Well, it should be very, very close to the population mean. So the sampling distribution has the same mean as the population. Okay. Suppose we have a large population with mean 82, standard deviation 7.2. Let's say we randomly sample 100 values from this population and compute the means and repeat the sampling process 10,000 times. Which of the following is the best approximation for the standard deviation? Well, that's just going to be the standard deviation of the sampling distribution, which is sigma divided by the square root of your sample size. 100, not 10,000, 100, 0.72. So if we have a large population with mean mu is 80 and standard deviation is 7.2, we sample of size 100, do it 10,000 times, which is the best approximation for the mean of our 10,000 sample means. I'm going to say it's the one that's closest to 80, because your sampling distribution should have the same standard or the same mean as the population. None of these are 80. I'm going to say it's at least probably 91. It's the one that's closest to 80. But I'm going to go ahead and tell you that this question has a mistake on it. So I'll address it. I'll bring it up when I'm done recording this. But the answer to this question should be 80. I just checked the code. I just paused it and looked at the code of the problem. And this value is set at 80. It should be randomized to match these. I'm just going to stick to 91 being the answer because it's the one that's closest to 80. But 80 really should be an answer choice. So I'll address it. I'm doing this video a week before you guys are even doing this assignment. So hopefully it'll be fixed by the time you do the assignment. But if not, I'm so sorry, but that should be 80. All right, the package of a particular brand of, I am tired of talking. I'm so sorry if I'm sounding bored. The package of a particular brand of rubber band says that the bands can hold a weight of 7 pounds. So we decided to take a random sample of 36. The mean breaking weight of our sample of 36 is 6.6. Assume that the standard deviation of the breaking weight for the entire population of these rubber bands is 2. Finding a random sample with a mean this low in a population with mean 7 and standard deviation 2 is very unlikely. Let's look. The standard deviation is 2. Let's just look at it. So n is 36. Let's just calculate that probability. N is 36. We want our mean is 36. Oh wait, no, our mean is not 36. The mean is 7. Sigma of the population is 2. That means the standard error, or the standard deviation, is equal to 2 divided by the square root of n. Let's calculate a z-score. So z-score here is, we want finding a random sample with a mean this low in a population of mean 7 in standard deviation is very unlikely. Well, let's just see. So our z-score is, we calculated a mean of 6.6. So let's just find the z-score for that. 6.6 minus 7 divided by the standard error. And let's just see, what's the probability that if we conducted another sample that we would get a value less than 6.6? So we can do norm S dis, negative 1.2. Cumulative value is 1. Well, what this probability tells us is that if the mean of the distribution really is 7, and there really is a standard deviation of 2 in that population, there's an almost a 12% chance that we would get a mean less than 6.6. So getting a mean of 6.6 actually isn't very unlikely. So that's going to be false. The bottle of Maria's favorite sports drink says that it holds 20 fluid ounces. Maria suspects that the sports drink actually holds a different amount. She takes a random sample of 25 bottles, so that's N. And mean is 20. The standard deviation of the population is still 2. This high in a population would mean 20. So that means we're looking now for the probability that we're greater than her sample mean of 21.5. Let's change our z-score. We want to find a z-score for a sample mean of 21.5. So 21.5 minus 25 divided by the standard error, which we already calculated, which is approximately 0. So, is it very unlikely? Yes. All right. Consider sampling height from the population of all female college soccer players in the U.S. Assume the mean height of a female college soccer player is 67, and the standard deviation is 3.5. Suppose we randomly sample 97 values from the population and compute the mean. Repeat it 5,000 times. Which of the following is the best approximation for the standard deviation of the 5,000 sample means? Well, this deals with means, so it's just, the standard deviation is just sigma of the population, so 3.5 divided by the square root of your sample size, 97. So 0.355, or 0.36. Okay. Consider the same situation, but which do you expect to have less variability? A sampling distribution with sample size 105 or sample size of 18? We should know this. We've talked about it a million times. Larger sample sizes have less variability. So the sample size of 105. What do you expect for the variability of a sampling distribution with sample size 6? It will have less variability than the population. Because remember, the standard deviation of the population is sigma. We're just dividing by the square root of 6. So it's going to be smaller, not much, but it will be smaller. Okay. Two bottling plants package a certain type of sports drink. Suppose the mean volume of all of this type of sports drinks is 20 fluid ounces. Bottling plant A bottles approximately 52,230 drinks per day. B approximately 179,478. Whoa. On a particular day, which bottling plant is less likely to record a mean volume of 21 fluid ounces for that day? Well, bottling plant A, because with fewer sports drinks, there will be less variability. The two bottling plants are equally likely. All right. I'm going to say, so bottling plant B has a larger sample size. So it's going to have less variability than bottling plant A. And with that number of sports drinks, more of its sample means are going to be at 20 fluid ounces with less variability. So that would be bottling plant B, because the daily mean will be closer to 20 fluid ounces with more sports drinks in the sample. More sports drinks means smaller variability. Suppose that the mean birth weight of human babies is 3,117 grams. Hospital A records an average of 59 births a day. Hospital B records an average of 10 births a day. On a particular day, which hospital is less likely to record an average birth weight of 341 or more? Well, that's going to be the hospital with the larger sample size, Hospital A, because the mean will be closer to 3,117 grams with more births, small variability. Okay, we have a histogram of a population with a mean of 1.7 and a standard deviation of 0.5. Suppose that 5 students each take a sample of 4 candies from the population, and each student calculates the sample mean for his or her 4 data values. Which of the following dot plots is the most plausible for the dot plot the students draw? Well, we do not expect one to be clustered super close together because our sample size is so small. So it's not going to be dot plot C, but we also don't expect it to be as spread out as the population. I'm going to go ahead and say that it's going to be A, because these still are really close together. We would expect, because our population is skewed like this, we're going to see many values between, 0.5 and 3. And because our sample size is so small, I'm going to go ahead and say dot plot A. All right, this is the same question. I'm just not going to do it. Okay. Figure A represents the weight for a sample of 26 pebbles, so each weighted to the nearest gram. Figure B represents the mean weights of a random sample of 3 pebbles each, with the mean weights rounded to the nearest gram. What is the difference between what is represented by the X circled in A and X circled in B? Well, in X, this plot here, each X represents 1 pebble. But in B, each X represents the sample mean of 3 pebbles. And that's the biggest difference. So, the X in figure A is the weight for a single pebble, while the X in figure B represents the average weight of 3 pebbles. There you go. They should be centered at the same value, between 5 and 6. 16. That's the same thing. Exact same question. Okay. A marketing student, number 61, is estimating the average amount of money that students at a large university spent on sporting events last year. He asked a random sample of 50 students at one of the university football games how much they spent on sporting events last year. Using this data, he computes a 90% confidence interval, which turns out to be 217 to 677. Which of the following conclusions is valid? We can be 90% confident that the mean amount of money spent at sporting events last year by the students at the university is 90% of the sample said no conclusions can be drawn. I'm going to say we can be 90% confident. It's random. He asked 50 students, yeah. A doctor is measuring the average height of male students at a large college. The doctor measures the height in inches of a sample of 40 male students from the baseball team. Using this, he calculates 95% confidence interval. Which of the following conclusions is valid? It can't be B because he only sampled baseball students. I think no conclusions can be drawn. It's not a random sample, so he can't generalize it to the college. Yeah. Okay, here we go. Confidence interval. All right. Students in a statistics class are conducting a survey to estimate the mean number of units students at their college are enrolled in. The students collect a random sample of 49 students. The mean of the sample is 12.2, and the standard deviation is 1.6. What is the 95% confidence interval for the number of units students in our college are enrolled in? Well, first of all, note that because we're using S, the sample standard deviation, we're going to use the T distribution. So we first need to think about what are our degrees of freedom. Well, the degrees of freedom are the sample size minus 1. So then we need to calculate the standard error. The standard error is S divided by the square root of N. And note, I'm clicking on the values because there are going to be more than one question like this on this review, even on your test. So having it all typed in, you can just quickly and efficiently calculate these new things. N, X bar, X, degrees of freedom, standard error. We now need to calculate the T star value. Because, with z-scores, we have a z-value, or with normal confidence intervals, where we're given the population standard deviation, we can just use z as 1.64, 1.96, all that stuff. But with t, you have to be a little bit careful. So we need to calculate what is the critical t value to calculate the margin of error. Well, we're going to use the t inverse function, and we want the probability. So we want a 95% confidence interval. So we need to think about how do we calculate this. So it's going to be 1 minus alpha, alpha being 1 minus 0.95, which is 0.05, divided by 2. And then the degrees of freedom is 48. And then we calculate the margin of error. That's going to be your standard error times your t value. Then we want the lower and the upper. So we do our lower value is x bar minus the margin of error. And then we do x bar plus the margin of error. And there we go. So rounded to 1 decimal, we go from 11.7 to 12.7. Our sample size is large enough, and the population is approximately normal. But we don't know anything about the standard deviation. That's why we're using T. So D. A statistics class is estimating the mean height of all female students at their college. They collect a random sample of 36. So I have everything typed in. So we're just going to change the numbers. Sample of 36. The sample mean is 65.3, and a standard deviation of the sample of 5.2. The only thing that we have to calculate then is our t-value, because we're changing our confidence to 90%. So if we go back to our t-star, it's t inverse minus 1 minus alpha. In this case, alpha is 0.1, because 1 minus 0.9 is 0.1. So our confidence interval is 63.8 to 66.8. A researcher is estimating the mean income of residents in a large city. The income variable is usually skewed to the right. She collected a random sample of 25 people. The resulting 95% confidence interval is that. Which of the following conclusions are valid, or is valid? We are 95% confident. 95% of the residents of the city have an income. Nope. And then no conclusions can be drawn. So with this question, though, because the population is skewed and our random sample is only 25, we really can't draw any conclusions because that sample size is not large enough. A doctor is measuring the mean systolic blood pressure of female students at a large college. Systolic blood pressure is known to be skewed. The doctor collects systolic blood pressure measurements from a random sample of 28. Same thing. But which of the following conclusions is valid? Alright. Yes. The sampling distribution of means will probably not follow a normal distribution, so we cannot draw a conclusion. What happened there? Okay. Justin and Haley conducted a mission to a new planet to study arm length. They took a random sample of 100 Planet X residents. They calculated a 95% confidence interval. What does a 95% confidence interval for arm length tell us? Well, I am 95% confident this interval includes the sample mean. No. I know that question is really weird looking, but it doesn't even matter because it's wrong. I am 95% confident that 95% of all, nope. I am 95% confident this interval includes the population mean arm length. That's all it means. Same thing here. Interpreting the confidence level. We are 90, let's say 68. Number 68. Alright, so it's the same thing. We are 95% confident that the interval contains the true population parameter of interest. Not doing 69 either. Not doing 70. We are 95% confident that the interval contains the true population parameter. Alright, 71. In a statistics class, each student surveys a random sample of 20 students to estimate the number of units these students at their college are enrolled in. The college population is 10,000. Using their data, each student constructs a 95% confidence interval from mu. The average number of units to 10,000 students at their college are enrolled in. There are 40 students in the statistics class, so there are 40 different 95% confidence intervals. Well, about 95% of the 40 confidence intervals will contain mu. That's what it says. About 5% of the sample means will not be included. Every sample mean is always in the confidence interval, so that's wrong. About each student's 95% confidence intervals will contain about 95% of the population. Nope. Yeah, it has to be A. Same thing. 73. A researcher took a random sample of 100 students from a large university. She computed a 95% confidence interval to estimate the average weight of these students at this university. The confidence interval was too wide to provide a precise estimate. True or false? The researcher could produce a narrower confidence interval by increasing the confidence level. False. Raising the confidence level widens the interval. True or false? These students could produce a narrower confidence interval by increasing the sample size. That is true. Increasing the sample size reduces the variability, producing a narrower confidence interval. Wow, they're really hitting home with this one. The students could produce a narrower confidence interval by increasing the confidence level. False. Making a wider confidence interval by increasing the confidence level. So increasing confidence level widens interval, increasing sample size narrows the interval. 76. The researcher could produce a narrower confidence interval by increasing the sample size. True. Suppose we take two different random samples from the same population of test scores. The population mean and standard deviation are unknown. The first sample has 25 data values. The second sample has 64. Then we construct a confidence interval. Well, which one's going to be narrower, have a smaller width, larger sample size, 64. The confidence interval based on a sample of 64 will be more precise. All right, I'm not doing 78. It's the same question. 81 values has less variability. I'm also not doing 79 or 80. All right. Man, they're really hitting home with this idea. Suppose we take a random sample of 41 state college students. We then measure the length of their right foot. We compute a 95% confidence interval for the mean foot length for students at this college. We get 21.71 to 25.09. Suppose we now compute a 90% confidence interval. As the confidence level decreases, the interval width decreases, increases, or stay the same. Decreases. As we raise the confidence level, we widen the interval. So if we lower the confidence level, the interval becomes narrower. All right. Same idea. I'm not doing it. I think 83, 84, 85. All right. Just calculating confidence intervals. You got this. Number 83. So I'm going to do probably one or two of these because once you get the gist of it, it's really the same question over and over and over again. Go down. All right. So students in a statistics class are conducting a survey to estimate the mean number of units students at their college are enrolled in. The students collect a random sample of 47 students. So N is 47. The students collect the mean is 12.3. The sample has a standard deviation of 1.9. So we're using the sample standard deviation, which means we're going to use the t distribution, which means we need to first compute the degrees of freedom, which is our sample size minus 1. We then need to compute the standard error, or the standard deviation of the sampling distribution, and that standard deviation is f divided by the square root of n. Now we need to get a critical, didn't mean to click that, whatever that was. We now need to compute t star, the critical t value. Remember, critical z values are, 1.645, 1.96, 2.5758, all that stuff for when we know the population standard deviation. But now we don't, so that's why we're using t. So remember, we're going to do, we want a 95% confidence interval. So let's just do confidence level is 0.95. So then we're going to do t star being t inverse. Our probability is 1 minus alpha, alpha being 1 minus the confidence level divided by 2. Degrees of freedom, 46. And this will allow the t value to change every time we get a new problem. So then we want the margin of error, from the margin of error, a lower bound on the interval, and then an upper bound. So our margin of error is the standard error times the critical t. Then we get our lower bound by taking our x bar minus the margin of error, and then we get it by doing x bar plus the margin of error. Rounded to 2 decimal places, so let's just lower that by 1, lower that by 1. So 11.74 to 12.68. Okay, So, same idea, we can do this one. A group of engineers developed a new design for a steel cable. They will need to estimate the amount of weight the cable can hold. The weight limit will be reported on cable packaging. The engineers take a random sample of 43 cables. The 43 cables have a mean breaking weight of 774.3 with a standard deviation of 15.4. And we want to know a 90% confidence interval. So I'm going to change my confidence level to 0.9. But because of the way that we type the problem, everything changes now. We take the standard error by just doing the sample standard deviation divided by the square root of the sample size. Our degrees of freedom is still n minus 1. T inverse, so the T star, the critical T is just 1 minus alpha over 2 in the degrees of freedom. And so it's 1 minus 0.1 over 2. The margin of error we still calculate as the standard error times T. And then we calculate our lower and upper by doing x bar minus the mean, or x bar minus the margin of error, x bar plus the margin of error. And then it's just 770.35 to 778.25. But I'm hoping, I know I'm kind of going fast with this, but you can only do so many of these problems over and over and over again, because it really is the same thing every single time. All you need are these values here to compute your confidence interval. So when you take your test, if you list it out just like I'm doing, when you get to, like, instead of having to do these questions over and over and over again, do it once and just change the numbers. I'll do the last one. Question 90. Is smoking during pregnancy associated with premature birth? To investigate, research selected a random sample of 130 pregnant women who were smokers. The average pregnancy was 265. Oh, and look at this. So with this question, we are actually given the population standard deviation. So with this question, it's actually a little different. So this idea is when sigma is not given. That's what we've been doing. But what about when sigma is given? So I'll do this whole thing. So we need basically n, x bar, sigma. We don't need degrees of freedom because it's a z-score. We need the standard error, confidence level, which we actually don't even need, z-star or z, margin of error, lower, upper. So you actually need less stuff if the population standard deviation is given to you. So here, random sample of 130 women, x bar was 265, sigma 16, so the standard deviation is sigma divided by the square root of the sample size. Z, we know it says is 2.575, which is what I told you guys earlier in the video. So that means the margin of error is Z times the standard error. And our lower is x bar minus the margin of error, x bar plus the margin of error. And there you go. I think when sigma is given, it's significantly easier because you don't have to worry about finding T, the degrees of freedom, all that stuff. Not very pregnant women who are smokers. Yes. So 261.387 to 268.614. Alright, so I know I didn't do a lot of the last ones, but they really do get to be the same type of question over and over again. So just pay attention to whether or not you're given your sample standard deviation, because if that's the case, you're going to use this idea of using T. If the sigma is given, the population standard deviation is given, just use the normal confidence interval way. So I hope this helps. Let's just submit it and see what happens. We all know I make mistakes on this often. So let's see. I won't have 100% and do all the questions. Just bear with me with that. 79. It's pretty good for skipping a lot. So let's just keep rolling. Let's go fast. I'm looking for red X's. Man, so far so good. I hope you guys like this section. I think this is super interesting. I think the idea of confidence intervals and what you guys are going to do next test is hypothesis test. Oh, I didn't do that one. But I think it's very interesting. I think it's so cool that we can generalize the results of these samples to the population. I didn't do that one either. I didn't do this one. Yes, I did. Let's see. Question number 57. It says I got wrong. Dot plot A has more chocolate. The dot plot of A is larger than the distribution of less variability in the sample means than in the original population. The standard deviation of the sampling distribution is, let's see, we have a dot plot. So I say it was A. Okay, so I gotcha. It is dot plot B. So with this question, we have our population. So in a sample with a standard deviation of 0.5. So in a sample of size 4, we would expect slightly less standard deviation. So that would make sense. We have our data spread out here. It will be a little bit less variable. So I would say it is dot plot B. Definitely not C. I didn't do that one. I didn't do that one. Wait, what? Okay, that's true. Question 61. I didn't read that. He wants to generalize this confidence interval to all students at the university. But because he sampled students at the football game, that is true. It is not a representative sample. So question 61, the answer is no conclusion can be drawn. Right? I didn't do those. I didn't do those. 71 is good. I didn't do that one. I didn't do those. Correct. I didn't do that. 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 How is the question 90? Rounded to 3 decimal places. I typed the number in wrong. Part 1 is right. Let's see. 261.387 to 268.614. That's right. I'll look at the code, but that is right. So, I hope this helped. I'm pretty excited right now that I only got 2 wrong. But, as always, if you ever need any help, please email your instructor. Email me, bpigeon1@gsu.edu. I teach the online class, so I'm not a student, so don't just do this for fun. I'm doing this to help you guys. But